This is kind of first stage research. This is kind of just getting going on a topic. Lydia Liu and Jorge Manny are students with me working on this. So we're going to talk about matching markets. It's a particular kind of market. It's not a market where there's prices being set. It's like a kidney exchange is a matching market. We want to simply match things together. And we want to do this in a learning context. All right, so kind of what's the minimal learning problem? To me, that's the multi-arm bandit. And not enough people talk about this. It's not supervised learning. It's not reinforcement learning. It's kind of the simplest problem, which is that there are K options. Here there's 3, and I'm a decision maker, and I've got to figure out which option I prefer. And I have no idea a priori which of the 3 is the best. So I pull the first arm a little bit, I pull the second arm and the third arm a little bit. And I start to see what reward I'm getting from each of the arms. And once I start to realize what looks best, I start to pull that more and more often. But if I kind of hone in too quickly on the wrong arm, I could pull it forever and really have a high regret. I could have pulled arm 3. That would have been better, but I too early opted for arm 1. So as you may know, there's algorithms like UCB, upper confidence bound, where you take not just the mean reward you've gotten, but you take a confidence bound on that, and you take the upper bound of the confidence interval and use that to decide which arm to pull. And so if you have a high confidence bound because it's really clearly a good arm, you're going to pull it a lot. But you might have a high confidence bound because you're very unsure about the reward. And you should also pull the arm for that reason. So this problem has embedded in it the exploration-exploitation trade-off, which is a core part of the learning problem that you don't have in supervised learning and you don't have in reinforcement learning, at least as it's traditionally done. So I think if you think about learning, that this is a great problem to be thinking about. Okay, so we pull, we get a reward, and we go back. So we're going to put that together with matching markets, and you all kind of know what they are. We've got buyers on one side, suppliers on the other, and they have preferences for each other. And Gale and Shapley introduced an algorithm that matches them up, that sort of give everybody their, you know, if not their exactly preferred item, gives everybody something they prefer enough that they wouldn't change, a notion of equilibrium. Now, so we're going to do this in a setting which is different from Gale and Shapley, where the buyers don't know their preferences because they haven't experienced the seller side of the market yet. They have to try it out. And the sellers don't know which buyers they prefer. They have to experience that side of the market. So we're going to blend together matching markets with learning. Okay, so the participants don't know what they prefer. So we have an exploration-exploitation problem, but in the context of other participants. So if I'm playing and I'm trying to pick the arm, but there's a bear playing too, we both might pick arm 2. And in our model that we've been studying, at that moment, what happens? Well, only one of us gets that arm. Okay, it's like going down a street. There's a capacity constraint. Not too many people can go down the street. So we model that by saying there's an exclusion. Competing agents have been modeled in economics, but it's more of a congestion channel. If both of us pick the same arm, neither of us get it. Okay, so let's suppose that only one of us get it. All right. And so how do we sort of set up this problem? And I'm going to kind of go quickly here just to say we've done this. You have to form a notion of regret. What's the best decision to make? Well, it's relative to the best you could have done. And so what we do is we define it relative to the best Gale-Shapley matching you could have if you know exactly all your preferences on both sides. And with that notion of regret, we're able to prove a theorem that a certain algorithm known as upper confidence bound Gale-Shapley, where everybody runs upper confidence bound and they send those numbers to a Gale-Shapley algorithm to do the matching. That algorithm has a logarithmic regret, which is sort of the best you can do. Moreover, the agents interact with each other in a particular way captured by this delta squared. Okay, so I think this is just an indication of lots and lots of research to come, at least certainly from my group, but I think lots of others, about how you put learning together in the context of systems that are trying to make multiple agents happy, not just a single agent happy. That's the real world to me, and that's what we need to be facing.